Current language models are built on an effective statistical foundation for generating smoothly flowing text, but look strictly at the underlying architecture, and that structure fractures. There is no comparable mathematical principle ensuring the factual logic. When a model confidently outputs a fabricated claim, it is directly exhibiting this missing logical framework. It is mathematically optimizing for the next plausible word, not deducing the next factual premise. The prevailing consensus in the engineering community is that fixing this by wiring strict, formal reasoning directly into neural networks requires computational power we simply cannot afford. To solve this, researchers are outlining a framework called knowledge infusion. It dictates that any knowledge a model learns must be structured in a specific form that makes principled, multi-step reasoning computationally feasible. Meeting this requirement involves a shift in how data is handled. Instead of forcing the model to guess how concepts relate through expensive attention layers, we run a pre-processing stage. We explicitly map the relationships between objects in the text before the learning process begins. Making the underlying data structures mathematically explicit helps ensure reliability, reducing the need for the model to guess at relational facts. This exact mechanism was formalized in a 2026 paper by Leslie G. Valiant from Harvard University, offering a practical architecture for enhanced and efficient reasoning in large learning models. His approach relies on a framework called robust logic. It is a quantitative computational model specifically designed to perform principled reasoning on information that has been learned and is therefore inherently uncertain. If you ask an AI whether Aristotle owned a coffee maker, it should not need to search its training data for examples of Greek philosophers using kitchen appliances to arrive at the correct answer. It should deduce the answer by chaining together two completely independent rules it has already learned: the timeline of ancient Greece and the invention date of modern appliances. Valiant achieves this through a specific data recoding method called the Unary Relational Integracode, or URI. With URI, the reasoning problem moves from a statistical anomaly to a polynomial time-learnable mathematical function. Consider a standard text processing window containing three distinct entities: Bob, Joe, and Sue. The text describes three specific actions occurring between them. Bob insulted Joe, Sue likes Joe, and Sue took revenge on Bob. This diagram shows how that natural language text is parsed and translated into a strict, robust logic conjunction. Every entity and action is explicitly mapped out as a formal variable. In robust logic, this explicit mapping happens in a workspace called the mind's eye, where the system actively holds these items and their formal relationships in a fixed state. It tracks immediate actions between individuals while also capturing overarching context indicators, like establishing that a specific set of artifacts belongs to the Bronze Age, which can span across massive distances in a text. In this architecture, parsing raw prose into strict mappings creates the foundation for reliable logical deduction. To feed these bindings into a neural network, a semantic analyzer first scans the text. It expands the standard base vocabulary of tokens, known as V, into a much larger specialized set, known as V'. A standard sequence of n text tokens expands downward into an h by n two-dimensional grid. Original tokens retain the top position. Beneath them, vertical slots receive augmented tags. Binary actions, like insulted, split into unary subject and object tags, anchoring directly into their respective token blocks. Binding these separated relational tags directly into specific physical token blocks forces the neural network to mathematically calculate connections without computing inferences from scratch. Once populated, this entire two-dimensional token grid operates computationally as a massive sequence of Boolean variables, zeros and ones. This Boolean equation formulates a strict equivalence rule for an action like revenge, isolated to Bob, Joe, and Sue. It falls into a structural class known as a 4DNF, or disjunctive normal form, Boolean formula. In computational theory, algorithms are measured by whether they can meet the standard of pack learning, which dictates what can be probably approximately correctly learned given finite data. The foundational theorem of integracoding relies on the proof that these k-DNF classes are mathematically pack-learnable in polynomial time, as long as the k variable is treated as a constant. Because chained reasoning rules reduce to simple k-DNF formulas, logical deduction transitions from a statistical hurdle to a learnable mathematical function with established error bounds. This explicit structuring resolves a major functional limitation present in standard LLM architecture during successive next token prediction steps. Every time a standard transformer completes a pass, generating the next word, it loses whatever internal relational data it gleaned during the previous independent step. The Integracoded architecture introduces a novel capability to solve this: explicit relational output. The URI system outputs the next word, along with the augmented tokens containing the V' relational data. This explicit relational output is carried forward intact and fed directly back into the neural network for the subsequent classifier call. This continuous, unbroken relay of explicit logic mathematically supports the chaining of independent rules over massive distances of text. The Integracode functions as a persistent computational working memory. It allows the model to execute multi-step deductions without suffering from relational amnesia between steps. Ultimately, offloading the logic shifts how we evaluate the hardware and energy costs of current AI scaling methodologies. This diagram's mathematical expression represents standard attention layers. They scale quadratically, demanding massive compounding energy for larger contexts. But by pushing relational heavy lifting to an explicit pre-processing stage, the neural network skips these dense attention matrices, achieving a drastically reduced computational complexity formula. As long as the block expansion factor h and the vocabulary expansion factor g' remain modest constants, the computing cost transitions from scaling quadratically to scaling linearly. Integrated coded machine learning offers a specific advantage. It replaces brute force scaling with a linear architecture that supports sound reasoning within rigorous probabilistic bounds.